Very good morning to you, students. Today I'm going to discuss one more theorem, that is the last theorem from reduction of coplanar forces. After that we come to the application of it. Okay, so here in yesterday's class video I have shown you that how a system of coplanar forces acting on a rigid body at different points can be reduced to a single force together with a couple, that is in analytical method. So we have seen that from that analytical method how we reduce all those forces P1, P2 acting at A1, A2, A3 up to AN, whose coordinates are x1, x2 dash dash xn with reference to the xy axis. We have reduced it to a single resultant R, okay, passing through this point O by introducing two equal and opposite forces for each of those forces P1, whose component force are x1 and y1 along the x and y axis respectively. So how we reduce it to a single resultant R together with a couple G here, whose moment, as we have seen yesterday, x1 y1 minus y1 x1. So now with that result we have obtained yesterday, how we reduce all those forces acting on a rigid body to a single resultant R together with a couple G. Now we are going to reduce these forces to either these two forces we have obtained, okay, that is the resultant R and the moment of the couple, to a single force or a single couple or a couple. We can reduce now these forces R and G either to a single force or a couple. And how we do that? So by analytical method, we have seen that we have this resultant R passing through this point O yesterday, okay. So if R is equal to 0, so we know that by analytical method we have reduced this system to a single resultant R acting at O together with a couple of moment G is equal to summation of x1 y1 minus y1 x1 by yesterday's video. Now this resultant R and this moment couple of a moment G is, we are either going to reduce it to a single resultant R or a couple, okay. This forces we have obtained yesterday, we are going to replace this R or G, replacing R or G by a single force or a couple. And how we do that? Okay. If this resultant R is equal to 0, so if this resultant R is equal to 0, then the whole system of coplanar forces reduced to a couple only. So this part is clear. If R is equal to 0, then this whole system of coplanar forces can be reduced to a couple only. Otherwise, if R is not equal to 0, how we replace this R here and this couple G by another force? So for that, by a single force, how we are going to replace this single resultant R and the couple G by a single resultant? So for that, you introduce two equal forces, one along, as this is the resultant forces we have obtained yesterday in the analytical method. So now we introduce to this point O another force along OB, okay, along the same line but in opposite direction. This is force R, okay. And then another force each equal to R, okay, opposite forces each equal to R along OB and opposite to that of the given force R, and another along O prime C, such that you take here, you draw another force parallel to the original forces R, that is R in the same direction, such that the along O prime, this is point O prime, C whose coordinate is HK with respect to the origin, such that O prime here is perpendicular. O prime is perpendicular. So here, let me draw it again just to make it clear. We have from analytical method how we reduce this whole system of forces yesterday to a single resultant R and a couple G of moment of that summation, okay. Now this force, if R is not equal to 0, so I'm going to introduce here now this the force R here and the couple, I'm going to replace it by this forces R along OB, This is B, okay? This force R along OB, and then by another force such that it is parallel to this. It should be parallel to this, and OO prime here must be perpendicular. This is point O prime whose coordinate is HK. This is another force R. So I'm going to reduce this resultant R and decouple G by a single resultant acting at O prime whose coordinate is HK, such that OO prime here is perpendicular to the line of action, to the line of action of this resultant R, to the line of action of R. So therefore G here in this case will be equal to R into the couple G, okay, is replaced now by this resultant R whose moment is equal to R into its perpendicular distance from these two forces, that is O into OO prime, or which implies that OO prime here will be equal to G by R. But what is G? From yesterday's method, analytical method, we have obtained G. It is equal summation of x1 y1 minus y1 x1 divided by R. So therefore the forces R at O and the couple G is equivalent now to a single resultant force R at O prime. So this R at O and the moment of the couple G, they are equivalent to a single resultant R acting at O prime. And let HK be the coordinates of R acting at O prime. Okay, the coordinates, or let HK be the coordinates of O prime. And since the direction of the force, given force R at O makes an angle theta with this, with the x-axis, this is the x-axis. So therefore, the direction of this R along O prime C, this is C, okay, along O prime C. So the direction of this force R also makes an angle theta with the x-axis. So therefore, the gradient of the line of action, or the slope of the line of action of R along O prime C. This is O prime and this is C. So the slope of this line, of the line of action along O prime C, is given by tan theta is equal to y by x. Okay, the slope of the line. You have come across this equation of straight line. How we define the gradient or the slope of a line in the xy axis. So therefore the equation of the line of action of the line of action of the final resultant at the point O prime whose coordinate is HK is given by this y minus k is equal to tan theta into x minus h. You have to use this equation of straight line, passing through x1 y1 with slope m here, that is the gradient tan theta with slope m here being equal to tan theta, is given by this formula y minus y1 is equal to m times of x minus x1. So using this equation of straight line here, the equation of the line of action of this force R prime or R along O prime C is given to be y minus k equal to, you replace this h and k by y1 x1 y1 and slope by tan theta. So we have here, so this implies that y minus k will be equal to, but what is tan theta? It is y upon x, y by x. What is the y here is the sum of the resultant forces, that is along the y-axis. We have solved yesterday y1 y2 plus dash dash, and x here is nothing but sum of the component forces along the x-axis, that is x1 plus x2 plus dash dash. So here instead of tan theta, you replace it by y upon x into tan theta, into x minus h. So after that, you cross multiply multiply that capital X to the left hand side, what you have is xy minus xk, okay, will be equal to yx minus yh, or xy minus yx, you bring it to this side, whereas this to this side you have xk minus yh, name it as equation 1. And as we have seen yesterday, those forces is reduced to a couple of moment g and resultant r. So g here is the algebraic sum of the moment of the forces about O, which is equal to summation of x1 y1 minus y1 x1. So if G prime is the algebraic sum, now if G prime is the algebraic sum of the moment of all the forces about, instead of O, now about O prime. So therefore G prime here will be equal to, instead of x1 you replace it x1 minus h, because about O prime whose coordinate is hk. So x1 you replace it by x1 minus h, and y1, small y1, you replace it by y1 minus k. So this is summation of x1 minus h into y1 minus k into x1. Okay, so which implies that, rearrange this, implies that G prime is equal to summation of x1 y1 multiply minus y1 into x1 into x1, and then minus h into y1, minus into minus. So sorry, I have put minus outside, so minus into minus, you will get this, that is plus k into x1. But what is this x1 y1 minus y1 x1? It is nothing but the algebraic sum of the moment of all the forces about O. So I'll replace this by G. So this is my minus, put the summation of h into y1 plus, minus into minus, plus summation of k into x1. So h and k, they are independent of the summation. You can take it outside. So we have h into summation of y1 plus k into summation of x1. But what is summation of y1? As we have seen, it is the sum of all the component forces along the y-axis. It is capital X, and here it is sum of all the component forces along the x-axis. So plus k into capital X, sorry, this is capital Y. Or you can write here kx minus hy will be equal to, bring this g to the left hand side, you have G prime minus G, name it as equation 2. Now using equation 1 and 2, what we get? What is equation 1? xy minus yx, okay, xy minus yx is same as hk minus yh. So this part you replace it by this value here, okay. So this value here you have obtained here in equation, to the left hand side you replace it by this value, because it is equal to xy minus yh. From equation 1 it is equal to this. So or you have here, or xy minus, I'm replacing this by using equation 1, minus yx will be equal to G prime minus G, name it as equation 3. So as we have seen that the final resultant in that given figure here, as the final resultant of this system of coplanar forces is passing through this point O, that is this one, this is the final resultant passing through O prime. So therefore G prime here must be, G prime must be equal to 0. So if G prime is equal to 0, what does it means? Equation 3 now implies, because the final resultant is passing, as I can draw here in the given figure, this is B, this is R, and this is R. So you introduce here final resultant C, this is O prime, This is R. So as the final resultant of row system is passing through O prime, so the moment of the couple that is at O, at this point O prime, that is G prime here, it is the algebraic sum of all the moments of the forces about O prime must be equal to 0. So we have equation 3 reduces to xy minus yx is equal to minus g, because this part is equal to 0, or you can bring this to this side. You have xy minus yx plus g is equal to 0, which is the equation of the line of action of the force. Okay, so this is nothing but the equation of the line of the forces acting at the point O prime, whose coordinate is hk. But in case, this is a case when r is not equal to 0. But in case r is equal to 0 and g also equal to 0, then all those system of coplanar forces, acting on this rigid body, will be in equilibrium. That is, they are either moving with uniform speed or they are at rest. Okay, I hope it is clear to you now.